Let's talk about the physics of why hair is curly. We can model hair as a long rod with natural curvature hanging down under its own weight. This is different than when you model, say, a spring with a mass hanging from it, because that mass hanging from the spring makes the force far more even. Whereas something like a strand of hair, which is hanging only under its own weight, has far more weight hanging from the top near the root than from the bottom of the strand. In this video, we'll explore the applications of such models, an example of some modeling, and some of the math behind it. Curled rods show up in the real world all the time. If you need to transport tubes or wires, they're usually wound around a large spool like this so they can be transported efficiently without getting tangled. This gives them a natural curvature, and that actually remains after they are unwound. So these models would help us represent something like this. There are many curled filaments subject to their own weight in nature as well. So having strong mathematical representations can help us understand the form of things like DNA and also plant tendrils or vines. Another place it shows up in nature is different hair types, which is what we'll be focusing on in this video, because being able to model hair has some really important implications. Let's take a look at some 3D animation clips. Here's Boo and Sully from Monsters, Inc., Rapunzel from Tangled, Anna and Elsa from Frozen 2, and Art from Monsters University. Take a look at the characters on the screen. What's missing? You can see that there's a lack of variation in the hair that gets represented in 3D animation. 40% of people have wavy hair and 15% have curly hair. But those people can't watch animations and find many characters whose hair looks like theirs. If this seems minor to you, think about the massive industry of hair straightening products utilizing heat and harmful chemicals to make hair straight. There has been a more recent trend of embracing natural curly hair, but that's been a challenge for a lot of people. When children grow up watching animated movies and shows and they don't see characters that look like them, it sends the message that they need to change in order to fit in. So along with diverse casting, in order to change this narrative, it's really important that we're able to represent a variety of different hair types so we can have more diverse characters appear in animations. Merida on the bottom right was one of the first major characters in 3D animation with curly hair. She's from the movie Brave, which came out in 2013. Part of the reason it took so long for this to happen is that it's challenging to mathematically model curly hair. If you look at the movement of her hair, it's not the most realistic. But notice the difference between Merida and the characters from Soul, which came out roughly 7 years later. And you can see that we've made a lot of progress. In large part, this progress has been made possible by researchers like Miller and Reese, who formed mathematical models for curly hair. In fact, most articles about animating curly hair refer to this paper. So we're going to follow along with part of their approach to solving this challenge. Here you can see a model which is in red and a scan in yellow of a single strand of curly hair. They took PVC pipes, filled them with stuff, and then wound them around something or laid them flat. Then they cured them, so now they have various rods with natural curvature. If there is no natural curvature, it just hangs down like this. If there's a little bit of natural curvature, you can see it starts to bend a bit. With more curvature, we see the tip start to rise upwards, and the more it curves, the less stable it is. Eventually, it falls out of the 2D plane and into the 3D plane. The reason it breaks into the 3D plane is because it's more energetically stable. This graph shows the elevation of the tip of a strand of hair as a function of the suspended length. You can see that it curves upward as it gets longer, and eventually it curves so far that it's almost past where the root of the hair is. That's around here on the graph. So that's really unstable. So to fix this instability, it breaks out and starts to curl around while hanging downward, rather than just hanging up. So if we follow that on the graph, let's look at this pink line, because that's the most curly of the strands shown. Here, the tip is getting higher and higher until it reaches its breaking point here, where it's really unstable. And then after that, it falls into the 3D plane, curling around and getting longer and longer. Now let's break down some of the math. The first term represents the strain energy, taking into consideration the natural curvature. The second term considers the gravitational potential energy. So when we plug in parameters to match our rod, this finds the energy at each point and integrates over the length of the rod in order to find the total energy. So it adds up the energy at each specific point. This tells us about the shape because the rod tends toward the lowest possible energy state. Looking at this graph, we're just going to focus on the red and green data points. Red is the simulation, so that's based on the equation we were just talking about, and green is what was actually found in their experiments. You can see they agree really well, which suggests that this is a good model for curly hair. This focuses on a single strand of hair rather than a bunch of interacting hairs, so it doesn't fully solve the problem of how to animate curly hair, but this was a major turning point in it. From here, 3D animators had a much better foundation, which supported all of the progress we've seen. So in conclusion, we've seen a mathematical and computer simulated way to model curly hair. It behaves like a rod with natural curvature, which is a system we also see in plants, DNA, and even industrial materials. The modeling of curly hair is important in the animation industry because without such models, there would be no 3D animated characters with curly hair. So this allows us to animate more accurate and more diverse characters. And it has applications beyond that as well. Thank you for watching. I hope you enjoyed exploring this cool piece of physics with me.